Imagine a commercial bakery, right? And suddenly the price of flour just skyrockets by like 1,000%.
Oh yeah, total disaster.
Exactly. I mean, they can't just stop using flour, obviously, and they definitely aren't going to start, baking bread with sawdust.
No, probably not a great business model.
Right. So what do? Well, welcome to today's deep dive, and that exact existential crisis is playing out right now across the entire global manufacturing industry.
Yeah, but instead of flour, the ingredient everyone is sweating over is this microscopic, highly specific metal called tungsten carbide.
Our mission today is to explore this completely invisible crisis. It's really a fascinating detective story about global economics, forcing some wild local innovation. We're looking at this industry report titled Strategies for Cost-Effective Machining Amid Rising Tungsten Prices.
Which I know sounds a bit dry at first glance.
Yeah, a little bit.
But it's actually incredible. Because, if you look around your house or your driveway, almost every physical manufactured object you interact with only exists because a tool made of tungsten carbide was able to, cut or shape it.
And joining me to translate these massive macroeconomic trends down to, the microscopic edge of a drill bit is our resident expert. So glad you're here.
Hey, glad to be here.
Yeah,
this report is just so compelling because it highlights how a supply chain squeeze is silently forcing some of the most genuinely ingenious engineering leaps we've seen in, a decade.
Okay, let's unpack this. Because to understand the solutions these engineers are coming up with, we first have to understand the trap they're in, right? Why is tungsten carbide the undisputed champion of metalworking? We've been cutting metal with other metal for centuries. What happened to just good old-fashioned steel?
Well, to understand that, you have to think about the physical reality of a modern factory. When you take a piece of metal and violently drive it into another piece of metal.
To shave it down, yeah.
Right. The friction is almost incomprehensible. And, friction means heat. Traditional high-speed steel was the standard for a really long time. But in a modern factory running at thousands of RPMs, the heat at that cutting edge can easily hit, 1,000 degrees Celsius.
Wow. 1,000 degrees.
Yeah, and under that kind of thermal stress, high-speed steel just softens. It literally deforms like warm butter.
Which I imagine completely ruins the precision of whatever part you're trying to make.
Exactly, you lose the tolerance. So enter tungsten carbide. It fundamentally changed the game. It's a compound made from tungsten and carbon, and its thermal strength is just extraordinary.
So it doesn't melt like butter?
No, it possesses vastly superior hardness and tremendous abrasion resistance compared to steel. It can take that blistering heat without losing its shape at all.
But reading through the report, it seems like engineers weren't even satisfied with that, because they mentioned taking this incredibly hard metal and coating it. How do you even coat something that's already one of the hardest materials we have?
Right. They do it through chemical and physical vapor deposition. They're applying a microscopic layer, sometimes just a few microns thick of material that is actually harder and more heat resistant than the tungsten carbide itself.
Wait, really? Like what?
Things like titanium aluminum nitride.
Okay, so you get the sort of composite effect.
Precisely. You get the tough, shock-absorbing core of the tungsten carbide underneath, paired with this extra hard outer shell.
Right.
And that shell resists wear and deflects the heat away from the tool.
And into the chips flying off.
Yeah, exactly. That specific innovation is the reason factories can run at the terrifying speeds they do today.
But here is the massive problem. The inciting incident for this whole report. Tungsten prices are just going parabolic. The supply chain is essentially in a geopolitical chokehold.
Oh, totally.
The report notes that China currently controls about 80% of global tungsten production. That is a staggering monopoly. It means their export policies and, internal mineral regulations effectively dictate the market price for the entire world.
Yeah, and you add to that a surging, insatiable demand.
Yeah.
The electronics sector, aerospace, defense, they are all hungry for tungsten.
Right.
So when you combine that soaring demand with geopolitical and supply chain disruptions acting as a massive bottleneck, the price inevitably skyrockets.
So this brings me back to my bakery analogy. If the flour is suddenly way too expensive, why hasn't the industry just swapped it out for something cheaper? I'm playing devil's advocate here, but if the drill bit is too expensive, just buy a cheaper drill bit.
What's fascinating here is that manufacturers aren't actually looking to buy cheaper metal. They are trying to preserve the value of their productivity. In the grand scheme of, say, a multi-million-dollar factory budget, the tooling, The actual consumable cutting inserts is a relatively tiny fraction of the cost.
How tiny are we talking?
Maybe 2 or 3% of the total machining cost.
Wait, really? Just 2 or 3%? Then why is everyone panicking over the price?
Because the performance of that 2% dictates the output of the other 98%. It dictates the speed of the entire factory line.
Oh, I see.
Yeah, if you swap to a cheaper, inferior metal to save a few bucks on inserts, your machines have to run slower to prevent the tools from melting. Tools break more often, which means unexpected downtime.
Which costs a fortune.
Exactly. Your overall productivity collapses. The financial cost of a factory running 20% slower far outstrips the money you saved by buying a cheap piece of steel.
Okay, that makes total sense. We can't step down in quality without destroying our margins. But what about stepping up? The report has this whole section on alternative ultra-premium materials, talks about ceramics and ceramics. If those have even higher heat resistance than tungsten, why aren't we just using those everywhere?
They do boast incredible hardness, but they introduce a pretty fatal flaw for general manufacturing. They are remarkably brittle. Yeah. Manufacturing isn't always a perfectly smooth, continuous cut. Often you have interrupted cuts. Imagine machining a metal cylinder that has a hole in it. Every time the cutting tool passes over that gap and slams back into the metal, it's a micro impact.
And because ceramics are so brittle?
They just shatter. They are highly sensitive to unstable machining conditions. Fantastic for specific, highly stable finishing operations, but they cannot handle the rough, heavy-duty reality of most everyday factory work.
Okay, so ceramics shatter. But what about the absolute top tier? The report mentions CBN, cubic boron, nitride, and PCD, which is polycrystalline diamond. Now, hold on. If we literally have industrial diamond tools, shouldn't that just slice through all our problems? I mean, it is diamond.
It sounds like the ultimate silver bullet, doesn't it? Just put diamond on everything. But if we connect this to the bigger picture, you realize that you can't just throw the absolute hardest material in the universe at a problem and expect a universal fix. Manufacturing requires a delicate balance of toughness, versatility, and cost. Those extra hard materials are astronomically expensive, and their application range is surprisingly narrow.
Narrow how? I mean, if it cuts, doesn't it?
Not at the molecular level.
Yeah?
Let's look at CBN first. It's fantastic, but it's restricted mostly to machining extraordinarily difficult materials. Things like hardened steels, cast iron, and high-temperature superalloys for jet engines. If you use it on softer, gummy materials, it's just a massive waste of money.
And the diamond tools, the PCD.
This is where the physics get really wild. You actually cannot use a diamond tool to cut a standard ferrous metal, like a steel engine block.
Wait, why not? Diamond is way harder than steel.
It is, but remember that 1,000 degrees of heat we talked about earlier?
Yeah.
At those extreme temperatures, a chemical reaction occurs. The carbon in the diamond tool literally dissolves into the iron in the steel.
Are you saying the diamond just melts into the metal?
Essentially, yes. It rapidly degrades chemically. So PCD is highly limited to non-ferrous materials like aluminum, copper alloys, carbon fiber. You use it to machine an airplane wing, not a cast iron brake rotor.
Wow. Okay, so tracking the logic here. We are well and truly trapped. Tungsten is too expensive, cheaper metals ruin our factory speed, ceramics shatter, and diamond tools chemically dissolve if you use them on steel. We literally cannot replace the tungsten carbide. So the industry had to pivot to a new philosophy, right? Using less tungsten, but making it work harder.
Precisely. They couldn't find a substitute material, so it forced a massive shift in physical tool design.
And this brings us to advanced coatings again, but in a different light. The report notes that new engineering allows tools to maintain the exact same life expectancy, even if they put less actual tungsten carbide inside them. But there's a catch.
There's always a catch. Applying those advanced coatings requires highly specialized vacuum chambers and complex equipment. So, you might save money on the raw tungsten commodity, but the process to apply the coating drives the final price right back up.
Right, so it doesn't really fix the core issue. Which brings us to what I'm calling the razor blade strategy. There's a brilliant Warren Buffett quote dropped into this report. Price is what you pay. Value is what you get.
Great quote.
Yeah. And it immediately made me think of safety razors. You know, you buy this nice heavy metal handle, but you don't throw the whole handle away when the blade gets dull. You just swap out the tiny engineered blade at the top. The industry is essentially doing exactly this, but scaled up for massive factory machines.
That is the perfect analogy. The industry calls it indexable tooling. Decades ago, a drill bit might have been one solid chunk of carbide.
Hmm.
Today, the main body of the tool, the handle of your razor, is made from cheaper standard steel.
And just the tip is the expensive stuff.
Exactly. Only the very tip, the insert making contact with the metal, is a tiny piece of precious tungsten carbide.
And what's fascinating is how the physical size of those inserts is shrinking. The report points to miniaturization. It explains this is actually being driven by how we make the raw parts before they even get to the machine.
Right. Modern fabrication methods, precision casting, advanced forging, metal injection molding, they've evolved tremendously. The raw chunk of metal arriving at a factory today is already extremely close to its final shape. They call it near-net shape manufacturing.
Meaning there is physically less metal that needs to be shaved off in the first place.
Exactly. If you only need to skim 1 millimeter off a part, you don't need a massive chunk of tungsten to do it. You can use a significantly smaller insert. The goal now is maximizing the number of usable cutting edges on one single microscopic piece of tungsten.
Let's look at exactly how this is being executed, because the real-world engineering is wild. The report highlights a leading tooling manufacturer called ISCAR and their blueprint for this. Let's start with milling and drilling. They have these two main product families, Multimaster for milling and SumoCom for drilling.
Right, those are the assembled tools.
Exactly. One steel shank holding various replaceable carbide heads. But I have to ask, if you make a tool out of two separate pieces screwed together, doesn't it vibrate? You just said vibration shatters tools.
And that was the huge engineering hurdle they had to overcome. It's a mechanical marvel, honestly. They engineered an extremely rigid clamping system between the steel body and the replaceable head.
How does it stay so rigid?
Through tapered threads and face contact, the connection is so secure that dynamically it acts like a solid tool. It completely resists those harmful vibrations.
And that rigid connection is what allows for their no setup time design.
Yes, and this is where the macroeconomic value really shines. When a cutting edge dulls, the operator doesn't have to pull the entire heavy tool assembly out of the spindle, measure a new one, program the lengths into the computer, and restart.
Which takes forever.
Right. They literally just unscrew the tiny carbide head and pop a new one on right there while the tool is still in the machine.
If I'm doing the mental math on that, you aren't just saving tungsten. You are saving machine downtime. If a factory line costs like $50,000 an hour to run, saving 5 minutes of setup time is a massive financial victory.
Precisely. Downtime is the most expensive commodity in a factory. ISCAR took this modular concept and started shrinking it down. The report lists specific lines, the Micro 3 feed for high feed, the Healy Tang, and the Healy 3 mill. These are portable cutters for square shoulder milling.
And some of these use a system called the FlexFit, right? It's a threaded modular connection. So you have one machine, but dozens of cutting profiles you can swap out.
It's all about hyperversatility without wasting mass.
Okay, so that's static milling and drilling, but what happens on a lathe where the metal itself is spinning at thousands of RPMs? The tool geometry has to change. The report covers ISCAR's turning lines, specifically the Logic 4-turn. And the spec here that jumped out at me is that it uses a tiny size 0.6 double-sided insert.
Very tiny.
But it somehow has 4 distinct cutting edges. It's meant for compact lathes and Swiss-type machines making, like medical screws. They also have the flash turn family.
The flash turn is a great example of physics driving design. It uses even smaller inserts designed specifically for shallower turning cuts. If you know you're only ever going to take a very shallow pass across the spinning metal, why use a long cutting edge?
Oh, that makes sense. Just shrink the whole thing.
Exactly. You drastically reduce the physical footprint of the insert, saving tungsten, but maintain the exact same performance.
This brings me to a section I really want to challenge you on: parting and grooving. This is when you plunge a tool directly into the spinning metal to slice a piece off. ISCAR has the Do Grip line. The report says it uses thin reversible inserts for precision cuts that are only between 0.8 and 1.2 millimeters wide.
Right.
That is basically the thickness of a credit card, like 0.031 to 0.047 inches. I get that it's thin. But does saving a tiny puff of metallic dust really impact the bottom line of a factory?
Oh, it absolutely does, especially at the scale of mass production. Think about the geometry of slicing something off. The width of your cutting tool determines how much of your actual workpiece is completely destroyed and turned into waste dust.
Ah, so it's not just about saving the tool material, it's about the material being cut.
Exactly. By narrowing that cut to under a millimeter, you're saving precious tungsten on the insert, yes, but you are also saving the expensive raw material of the workpiece. If you make 10,000 cuts a day, Saving 1 millimeter per cut adds up to massive lengths of expensive metal saved over a year.
Wow, okay, I hadn't thought about the volume of the waste.
Plus, when you are parting off thin-walled tubes, a wide, heavy cut will crush or deform the tube. A 0.8 millimeter cut slices through cleanly.
Okay, I stand corrected. Saving dust definitely pays off. But here's where it gets really interesting to me. The report highlights an evolution in this category called the pentacut.
Oh, the pentacut.
Just try and picture this in your mind. Think of a microscopic ninja star. It's a star-shaped mini insert with a 17 millimeter inscribed circle, so roughly 0.67 inches across. It has 5 completely distinct cutting edges on this one tiny star and makes cuts ranging from 1.5 to 2.5 millimeters wide. I just have to marvel at the pure geometric genius of a tiny 5-point star slicing through metal.
It really is an elegant solution. The multi-edged star design is the ultimate strategy for maximizing material. If one point of that tiny star gets dull while spinning, the operator doesn't throw it away. They just unscrew it, physically rotate or index the star exactly 72 degrees, lock it back down, and a brand new razor edge is instantly engaged.
5 tools for the material price of 1.
Exactly.
So we've made the tungsten replaceable, we've shrunk it down, we've maximized its edges with ninja stars. But the final section of this report details the ultimate evolution. If you simply cannot reduce the physical material any further, you have to make one tool do the job of 2.
Right. This is the rise of multifunctional tooling. We talked about how expensive downtime is. Every single time a machine has to stop, retract, put away a drill bit, and pick up a milling cutter, valuable seconds are lost.
Enter the quick demill. The report holds this up as the perfect example of an all-in-one solution. It literally combines milling and drilling into a single piece of hardware. Let me run through the specs because this sounds mechanically impossible. It's a double-toothed right-hand cutter. It uses 2 rectangular carbide inserts, and each of those inserts has 4 edges.
Right.
So how does one tool drill straight down, but also mill sideways?
It all comes down to how the cutting forces are distributed. When the tool is plunging straight down into solid metal, which is drilling, it operates using one effective tooth acting on the center to pierce the material.
Okay, I'm following. So it clears its own path downward.
Right. But once it is plunged to the correct depth and starts moving laterally sideways through the material, which is milling, the physics shift entirely. It now utilizes 2 effective teeth on the periphery of the tool to carve out the cavity.
That is brilliant. And it's available in diameters from 16 to 32 millimeters, so like 0.6 to 5 to 1.25 inches. And it even comes with a multi-master head configuration.
Yep, keeping with that modular theme.
And the kicker is it features an internal high-pressure coolant supply. It blasts coolant right through the center of the tool directly onto the cutting edge.
Well, it has to. Because if it's doing twice the work without ever leaving the spindle, it is generating immense heat. You have to evacuate that heat and the chips immediately.
So what does this all mean when we step back? When I look at a tool like the Quick Demill, it feels like the ultimate middle finger to rising global tungsten prices. They didn't solve the problem by finding a cheaper metal. They solved it by simply doubling the operational capacity of the tool itself.
This raises an important question about innovation in general. We tend to think of supply chain constraints as purely negative forces. But time and time again, we see that severe constraints are exactly what drive the most brilliant leaps forward. The skyrocketing price of a raw material in China didn't destroy the machining industry. It forced it to become relentlessly efficient at a microscopic level.
It is truly a masterclass in adaptation. So to bring this all together for you listening, we started with a massive, invisible global crisis. Geopolitics clamped down on tungsten carbide. But rather than accept defeat, engineers completely reimagined the physics of cutting metal. They invented highly modular, multifunctional, star-shaped geometries and fully embraced the razor blade strategy.
It's a powerful reminder that true value isn't just about the market price of a raw material. It's about the human intelligence applied to that material.
I absolutely love that. And that brings us to the end of our journey today. But before we sign off, we want to leave you with a lingering thought.
Yeah, think about the ripple effects here. If a geopolitical squeeze on something as specific as tungsten could silently force this much rapid innovation in a simple factory drill bit, what other everyday hidden technologies in your life are quietly being revolutionized right now simply because a raw material became too expensive?
It's definitely something to mull over the next time you hold any manufactured product in your hands. Thank you so much for joining us on this deep dive. We appreciate you taking the time to learn with us, and we'll catch you on the next one.